Hello, everyone. This is Chunxiang Yan, a backend engineer from Yum China. Today, I'm honored to share the details of how we use Pulsar to support our business in Yum China. This sharing will be divided into the following parts. We will have a brief introduction of ourselves and why we choose Pulsar as our main MQ solution. After that, we will show you our architecture together with some use cases of Pulsar which we found worth sharing. And then, based on those use cases, we'll share our performance tuning experience and also we'll show you two gotchas in our daily usage of Pulsar. And finally, our future plan. So let's get started. This is an introduction of myself. My name is Chunxiang Yan. I joined Yum China as a backend engineer in 2021. Since then, I have been responsible for maintaining and evolving of our Pulsar paths. During this time, we accumulated some knowledges and practices of using Pulsar, and therefore, we are here to share them. This is an introduction of my company. We, Yum China, are the largest restaurant company in China. We have over 12,000 restaurants spread over 1,700 cities. We have more than 400,000 employees, and our annual customer goes beyond 2 billion. Our software engineer team is based in 3 R&D centers located in Shanghai, Nanjing, and Xi'an. Below is a list of our brands. I hope some of them looks familiar to you. Enough about us, let's start our sharing. Why Apache Pulsar? This is a question I often heard. The actual decision goes back to 2019. Back then, we wanted to build an MQ path for our internal usage. However, we did not know how much traffic we should expect. And therefore, horizontal scalability becomes a crucial feature in our case. And also, because we will have to operate this cluster ourselves, operational cost is considered important as well. So based on these two requirements, we compared Pulsar with Kafka and RabbitMQ. These are two MQ systems we used internally before Pulsar. And we concluded that Pulsar, with a better design principle, will outperform these two in terms of scalability and operational cost. This aside, the fact that Pulsar is still a very active evolving solution also attracts us a lot. We find features like different subscription types, guaranteed message delivery, low publish latency, and seamless geo-replication are all extremely helpful in our practices. We'll actually show you some use cases we have where these features comes in great help in our use case introduction section. All this becomes a reason which finally lead us to choose Pulsar, and we are happy with this decision ever since. Now, let's start our use case introduction session. Before we massively jump into Pulsar, we analyzed our MQ traffic. We noticed that, based on their characteristics, our traffic can be divided into two kinds. The first kind is a core business data, where data integrity, throughput, and the publish latency becomes very important. The cost effectiveness of the cluster is less a priority. And the other kind of data is operational data, which in our case is basically monitoring metrics. And for those monitoring metrics, we don't really care much about the integrity and latency since they are naturally ephemeral data. In their case, the cost effectiveness becomes important. So we have to hold all of our traffic with a relatively small setup of hardware. And also, we have actually tons of monitoring metrics. So the issue becomes even more challenging as we will focusing on how to reach the maximum throughput to contain all of our metrics. So based on this observation, we set up our cluster differently for different kind of data. For the business data, I'll refer the cluster as a biz cluster. And for the operational data, I'll refer to the cluster as a ops cluster. And let's start to reason the difference we have in configuration. Well, the very first and the obvious difference is the size of the cluster. We have 26 nodes in the base cluster and only 10 nodes in the ops cluster. This difference will contribute to the difference in throughput, and naturally the base cluster will have a better throughput. And the second difference here is a different send method we use. For the biz cluster, we go with a synchronous send, and for the ops cluster, we go with the asynchronous send. Well, asynchronous send will naturally perform better in terms of publish latency and overall throughput, but it has one significant flaw. When you call the async send method, the Pulsar client will actually put this message into a local send queue and wait to be sent in batch to Pulsar server. And therefore, if you experience some service crash or power failure, those messages in the send queue will get lost. And this is intolerable in our core business scenario. So we basically sacrifice some publish latency and throughput by using the synchronous send method. And this is basically to ensure the durability of our writes. The third difference here is a quorum setting. The write quorum here simply means the maximum replication for your message. And the act quorum here, it simply means the minimum replication for your message. With the write quorum as 3 and act quorum as 2, we guarantee that every message in our biz cluster will have at least one copy. And for the ops cluster, as we mentioned, it's basically monitoring metrics and they are naturally ephemeral. So we don't need any replication for them. The last difference here is how we configure the journal write behavior. Some background on this. When you write a message to Pulsar, it actually gets stored into Bookie, and the Bookie will store your message in two places. The first is the journal file, which is used as a recovery measure. And the second is a ledger file. And this is where your message is actually persistent and you will read from it later on. So if you turn on the journal sync option, and by default it is on, your data will be persisted to the hard drive before your write request returns. If you turn it off, then the data will be read to the operating system page cache and your write request will return. And then at that exact moment, if you have power failure or system reboot, those messages in the operating system page cache will not be able to get flushed into the actual hard drive, and therefore you will lose those entries. And again, this is intolerable in our core business scenario. That is, it works just fine for our ops cluster. So with this setup, in the biz cluster, we address the throughput issue with horizontal scalability. And we address the data durability issue with all these configurations below. The remaining issue is the latency. And actually, some of this configuration adds up to your latency. And we will show you how we actually lower our latency in our biz cluster in the performance tuning part. And also for the ops cluster, we basically throw away all guarantees for the data durability, but the throughput still remains a very challenging problem. And we'll show you how we reached our maximum throughput on the configuration on the client side. Now let's look at our overall architecture. In Yum China, we have 4 active zones. Each active zone runs a copy of our entire working system. We deployed 2 Pulsar clusters in each active zone, one for the biz cluster and one for the ops cluster. Uh, all of our biz cluster are connected with a geo-replication namespace. And based on this setup, we managed to build some very interesting services, which we will show exactly later. Okay, let's first look at how we handle our operational data. I assume everybody knows Prometheus. We use Prometheus to store all of our monitoring metrics. And what's more, we want our monitoring metrics as stream data, so our big data engineer could analyze those streams. And then they will probably make some automatic operational decisions. For that purpose, we developed a component called Nightingale. This component is inspired by an open source project, Prometheus Kafka Adapter. What Nightingale does is that it basically receives a Prometheus remote write, and the message will look like this struct. And the Nightingale will extract the field called the time series. We will reformat this time series into our customized data format, and then we will put them back into Pulsar. As you can see clearly that all our monitoring metrics will go through Nightingale. So Nightingale becomes a case where throughput matters. We actually reached 200,000 messages with 3 nodes setup of Nightingale. And we will show you in the performance tuning part how we managed to do that. Another case we'd like to share is a service we named Pigeonhole. Pigeonhole is a service we built to replicate message between heterogeneous MQ system, which in our case is basically Kafka and RabbitMQ. With the help of Pigeonhole, our developer could only focusing on handling the actual message, and they will only write one consumer for the message, for example, a Pulsar consumer, and all other messages in Kafka and RabbitMQ can be replicated with the help of Pigeonhole. Pigeonhole is also the case where throughput matters. We managed to reach 50,000 messages per second per node using the same optimization logic in Nightingale. Another interesting case we would like to share is how we use digital replication, and it is Sonic. Sonic is a SaaS we built to sync Redis command to different active zones. The design logic of Sonic is that it will receive Redis command from the client and wrap those Redis command with extra information we need. Then put them into a Pulsar's geo-replicated topic. And we will have other instances in other active zones, and those instances will consume the replicated message, and then unwrap those messages and execute the Redis command into their local Redis cluster. With this setup, we actually achieve the broadcast of Redis command to all active zones. So with the help of geo-replication, we freed ourselves from the trivial detail of data durability arrangement and replication process. So we built Sonic with only focusing on wrapping and unwrapping of Redis command. Since Redis is a naturally fast service, we want our Sonic to match the latency requirement, and therefore, latency becomes very important performance metrics in this case, and we will share our attempts to lower the published latency in our biz cluster. The last use case we have for today is Event Bridge. We build Event Bridge to gather events in our cloud system. And then anyone who's interested in those events could grab their copy by creating a subscription together with some filtering rules. Event Bridge system is composed with three key components. The first is a processor. It will accept all incoming events and put them into a Pulsar's Event Bridge topic. And there will be rule engine which consumes that Event Bridge topic and will do some rule matching, and those matched events will be put into the send topic. Then the event processor will consume the send topic and send those events to the actual subscribers. In Event Bridge, different subscription types actually helps us to provide different level of guarantees for each subscriber. As you can see here, we use a combination of different send method together with some different subscription types to give guarantees for ordering and persistence of events. Now we basically wraps up all the use cases we'd like to share. And as we have discussed for the bits cluster, the published latency is a remaining issue, such as in Sonic's case. So we will share next our experience in reaching low synchronous publish latency in our base cluster. But before we go to the details, let's cover some basic concept first. When a message is written into Pulsar, it's essentially written into Bookkeepers. And in Bookkeeper, your message is actually write into two files. The first is a journal file. It's basically a transaction log of all your writes. And the second part is a ledger. And the ledger is actually where your message will be persistent, and you will later read from the ledgers. So this graph actually shows the whole process when you write a message to Bookkeeper. The upper part is how Bookkeeper handle a write to the journal, and the lower part is how Bookkeeper achieves a write to the ledgers. A write to the ledger is totally asynchronous, so it does not add up to your latency, and it actually allows for some data loss in case you have a reboot of the service or crashed app. And the process on top is where Bookkeeper writes to the journal, and it's a synchronous process, and it will add up to your latency. The steps over here is basically writing to a local queue and read by another thread. So this does not contribute too much to your latency. Well, the process we need to look at is this fsync call. Basically, by calling this, Bookkeeper asks your operating system to do a flush of its page cache. And we actually mentioned this in the configuration about the journal sync options. If you turn the journal sync option on, Bookkeeper will do a fsync call for every write. And the latency of this fsync call will heavily depends on the performance of your hard drive. So based on this background knowledge, what to look for when you have high latency in your system? Well, we recommend you to check for three places. The first is your hard drive. As mentioned that the fsync process will heavily depends on the performance of your hard drive. So it's very smart to check them first. The second thing you need to pay attention to is actually the GVM GC Pulse. Well, because Pulsar is naturally a Java program, and every Java program suffers from GC Pulse. And finally, some heavy process in Pulsar. Pulsar is a very complex system, and anytime there is a tons of running processes under the hood. And you probably need to spot the correlation between your high latency and some triggering of the internal processes. Well, luckily, we have an example for all these three cases, and we will go through them one by one. First is a hard drive, of course. Different types of hard drive tends to have dramatically different performance metrics. And this is a benchmark I grabbed from the internet. And you will see that the SSD drive outperforms the physical hard drive 5 times. So, how do you know if your hard drive is any good? Well, we recommend you to do a FIO benchmark on your hard drive. FIO is a very easy to use Linux command line tool. You basically specify your IO engine to be sync, and you turn on the fdata sync option. The whole benchmark will simulate the process where Bookie writes to the journal. And this is a screenshot of our problematic instance. Now you see here that the maximum latency for a fsync write actually reaches 60 milliseconds. This is beyond expectations for a SSD instance. So with the information from our FIO benchmark, we discussed with our cloud provider. And we believe that the issue lies in the network switches. So we basically decided to switch to a local SSD setup. And the result turns out amazing. Our maximum write latency drops from 300 milliseconds to 5 milliseconds. So always check your hard drive first. It will pay off significantly. Now let's look at the case for GVM optimization. But before we jump into the params, we recommend you to use the Pulsar Grafana dashboard provided by Stream Native. They have a board specifically for GVM metrics. And there you could see your duration of GC pulse easily. And the showing instance actually have a relatively high GC pulse, around 150. This is definitely suboptimal, especially in the case where latency is important. So if you look at the default GVM setup of Pulsar, it's actually a throughput-oriented setup. It asks for very large new generation size, and it has a very large concurrency for GC threads. Well, this will work well under heavy load. But in our case, we don't have extreme heavy load, and latency is important. So we fine-tune these params to remove the new generation requirement, and also lower the concurrency of GC threads. Uh, there is a very interesting point worth mentioning. With the G1 garbage collector, it will try to adjust its memory slot to match the specified maximum GC pulse. If you ask for a specific amount of new generation space, it will fail to reach your requirement here. You will see that our instance have a GC pulse of 150 milliseconds, even we ask for them to keep the GC pulse around 10 milliseconds. So by removing the new generation requirement, our GC pulse becomes normal again around 10 milliseconds. And with this configuration, our maximum publish latency drops from 500 milliseconds to 100 milliseconds. It's quite some improvements. All right, the last case is about the internal process of Pulsar. So we noticed that we have high publish latency in a periodic fashion, namely exact same time every week. And the latency is actually really high. It sometimes gets beyond 5 seconds. And this leads us to the bookkeeper log. At that exact moment, we see this line. The auditor bookie is trying to start a process called check all ledgers. So what is it? Well, to answer this question, we need to first introduce a concept of auditor. Auditor is one of the elected bookkeeper node responsible for your data integrity checks. The check all ledgers process will be carried by the auditor node. It will scan all your ledgers to see if your ledgers are replicated enough to match the red quorum requirement. Of course, this process will take tons of read and write operation on your hard drive, and therefore it will increase your latency. Luckily, we have a way around this, as check all ledgers check by default runs once a week. If we set the trigger time at night, it does not influence our business anymore. So the command on the right is a command to force trigger the process. If you execute this at the night time, then the next time the process will be triggered at night. The second process we need to mention is the entry log compaction process. Well, because Bookie stores ledger in a interleaved fashion, so in a entry log file, you will have deleted ledgers and mixed with undeleted ledgers. If there is some undeleted ledgers, the entry log file itself cannot be reclaimed. Thus, it becomes a waste of your storage space. How Pulsar tackles this problem is by creating a garbage collector thread, and it will scan all your entry log. If it finds that there is some undeleted ledgers, it will move them to a new entry log file, and then reclaim the old entry log file. Well, this process will save you some disk storage, but it involves a lot of read and write as well, and therefore it will add up to your latency. Luckily, Bookie provides options for us to throttle this process. If you turn the throttle on and specify the limit you want to throttle the process, you will most likely be safe. So this wraps up our efforts to reach low latency in our base cluster, and we are happy with the result ever since. But still, there is a remaining issue. is how to reach maximum publish throughput in our ops cluster, which we will go through now. To reach maximum throughput, there is a simple math you should consider. If you use a synchronous send process, and your throughput will highly be limited by the round trip time of your network. Say if you have a round trip time around 5 milliseconds, then the total throughput of your service will be no more than 200. And therefore, we need to use synchronous send method to fill up the water pipe. The graph on the top shows how Pulsar handles the send async call. By invoking the send async method, the client will put the message into a local send queue. And then there will be another IO loop thread scanning this send queue. If certain conditions are met, it will do a batch send and put those messages to the Pulsar cluster. On the bottom left, you have some metrics to tweak on the client side. And with this configuration, we actually reach 46,000 messages per second per node in our Nightingale instance. The first line of this configuration simply means the size of the send queue. If the messages in the queue reaches the maximum pending messages, it will either stop your producer or it will throw an error, depends on your configuration. The second configuration here is how long the first message will wait in the queue. So setting this to 1 millisecond basically means that this IO loop will do a batch send every 1 millisecond. Then there is compression configuration. It's basically trading your bandwidth with CPU power. And the last thing is to limit the size of your message batch. Of course, this configuration is not universal. We would suggest you to start with our settings and try out what works best for you. Well, at least we are happy with the throughput we can reach for now. Okay, as promised, we will show you two gotchas in our daily usage of Pulsar. The first gotcha we have is a block consumer. We have a service triggered by HTTP request, and upon triggered, it will get or create a new consumer, and then receive all messages in the subscription backlog. Upon consuming all the messages, the consumer will stop consuming, and the HTTP call will actually be returned. One day we found that this service does not consume message anymore, even there is actually backlog. So the gotcha here is that the Pulsar will push message to your consumer local queue. And by calling the receive function, the consumer actually take message from this receiver queue. If your consumer does not call the receive method, this message will stay in the queue, and no other consumer will be able to consume them. So, well, now we know the cause of the problem. The fix is relatively simple. Just close your consumer if you don't need them anymore. Another gotcha we met is a crashed consumer. This happens during the load testing. Our service just keeps crashing with out of memory error. It turns out that it's an issue with the receiver queue again. By default, the receiver queue is of 1000 messages. So if you have a relatively large backlog and your message is relatively large, say 1 megabyte, then this receiver queue will totally consume 1 GB of memory. And this in a normal scenario of a microservice is a lot of memory, and it will easily cause out of memory when your service is under heavy load. So be very careful with this. Okay, the last thing we'd like to discuss is our future plan on evolving our Pulsar path. The first thing we'd like to do is to put our Pulsar onto Kubernetes to embrace the cloud native practice. But this will be a continuous process because we have a lot of Pulsar on virtual machine, and a lot of our critical services depends on that. The second thing we'd like to do is to set up a infrastructure as code setup for managing our Pulsar configuration. And we saw that the Stream Native actually published a Pulsar Terraform provider, and this will come in great handy in our case. Well, this basically wraps up our today's sharing. Hope you enjoyed the content and looking forward for your feedbacks. And wish you enjoy the coming up sessions as well. Thank you.